Today it's all about the new RoadPak module from Hitachi Energy, an E-Mobility Power-Modul with a future-proof supply chain. My name is Erik Rehmann and I am responsible for marketing at GVA in Mannheim. Our technical presentation today will be given by Tobias Keller. Tobias is Vice President and Head of Global Product Management Semiconductors at Hitachi Energy in Lenzburg, Switzerland. This webinar is part of our expert series in which we are happy to share our knowledge and that of our partners on new products, technologies, and findings from the field on a regular basis. Also check out our website gva-power.de and register for the webinars that interest you. Or simply visit our YouTube channel and watch the video recordings at a later time. During the live webinar, please feel free to use the chat function of our online portal and ask your questions. We will be happy to address them after the presentation. But now we go live to Tobias Keller in Lenzburg. Tobias, I hope you can see and hear us well.
Hello, good morning, good afternoon, good evening, everybody. I can hear you loud and clear. I hope you can also hear me.
Yeah, that's very good.
Okay, thanks a lot. It's a pleasure for me today to talk about our RoadPak, the Hitachi Energy RoadPak, and give you some more insights on the RoadPak itself, on the reliability, as well as on the supply chain. Good, let's start with a short introduction. I called it the 3 things good to know at start. My name is Tobias Keller. I'm located in Lenzburg in Switzerland, as already mentioned. And I started 23 years ago in the power electronics industry. I'm very passionate about sustainable solutions with power electronics and mountains in my free time. And you can reach me on the email address just shown here. Maybe also important to mention at the very beginning, short wrap up on Hitachi Energy. You might know us still as ABB Semiconductors. Nevertheless, we have changed the name quite some time ago, more than 2 years ago. We are a global player for sustainable transmission, mobility, and distribution solutions. Currently, we are a joint venture owned 80.1% by Hitachi, 19.9% by ABB. Starting 1st of January, as recently announced, we will be 100% Hitachi. The Hitachi Energy as company has 30,000 employees in more than 90 countries and the headquarters in Zurich in Switzerland. Hitachi Energy Semiconductors, we have more than 100 years experience in developing, manufacturing and testing power semiconductors. And this expertise is mainly based on the 2 pillars, HVDC, high voltage DC link transmission and distribution lines, as well as on traction. And we decided some years back to take all this experience we gained in these both fields, being able to produce highly reliable, high power devices, and to start with the development of an e-mobility power semiconductor. Today, the presentation has 3 parts. First part is really an explanation on the RoadPak as a platform. It's not only one module we see later, but it's a complete platform. This platform is also intended for more than just one application, but it's for a wide range of application. And what is very important in many of these applications, and what also perfectly fits to our past experience from traction as well as from HVDC application, is of course reliable solution, and therefore RoadPak is suitable for mission critical applications. As you all know, there is a huge growth in e-mobility. There is a complete change just happening now, a transformation from combustion engines to more electric drivetrains in cars, in e-buses and e-trucks. At the time when we as Hitachi Energy decided 4 years ago that we go for an e-mobility module, we made a drawing for us to understand the whole situation. It's very obvious we are talking about drivetrains. We are talking about different power levels you require for cars, for e-buses, e-trucks. And we set a clear mission statement and said, okay, we want to develop a platform for power semiconductor that is able to drive 100 kilowatt to 500 kilowatt axles, either one axle or two axles, to be able to support various power. That's coming even more important in the meantime, again, with different power on the both axles, like a boost axle, a second axle, and the primary axle driving usually during normal operation. Then support both battery voltages, the 400 volt as well as the 800 volt. Even we see now more and more that it goes towards 800 volt with all of the advantages of fast charging as an example. Nevertheless, you will see also that we're still supporting the 400 volt battery system. 4 years ago, there was a very uncertain situation in regards to the spread between silicon and silicon carbide. I think that has kind of stabilized a lot during the last few months. There is a clear drive, 800 volts towards silicon carbide. Nevertheless, due to some capacity limitations or possible capacity limitations, there are various players also thinking about a silicon second axle. And therefore, we are also supporting both silicon and silicon carbide with the RoadPak itself. Obviously, it's important to support different cooling topologies to be able to provide a solution what is required at the end, what fits into the space, what is available, therefore support different cooling topologies. As we are using as one of the main target silicon carbide, it is obvious that most appropriate connection technologies have to be used. We'll also see that later on, and also to use an improved electromagnetical design. Silicon carbide is a lot about stray inductance to keep it as low as possible, and we have done here extraordinary efforts to get the stray inductance as low as possible. Furthermore, it's important to cool down the silicon carbide chips as good as possible. Therefore, also focus on an optimized superior thermal design. Good. Let's go into the family. Let's have a look at the RoadPak family at the platform. We call it the Power Beast. You will see it also if you have a look at the largest module, the so-called L size. We made it very simple. It's like t-shirt sizes, small, medium, large, S, M, and L. The large size at 1200 volt, it is a 2x10 chip setup. That means we are supporting up to 980 amps. Therefore, it's really, you will understand why we call it the Power Beast. It's being able to scale down, not having only 2x10 chips, but also have 2x8 or 2x6 chips, what we then call S, M, and L size. All these, the three different sizes, S, M, and L, they have the same outer package dimensions. That means it allows you to build one converter and use always the same outer dimensions. Of course, especially the reduction on the chip numbers helps us also to be very cost optimized, what leads to competitive pricing. What is important to keep in mind here, and it's also one of the targets and one of the topics already addressed in the title of this seminar, there is a lot of thoughts and a lot of discussion currently on security of supply on silicon carbide. We invested quite a lot of time and quite a lot of efforts exactly on that to make sure that we can deliver these RoadPaks, considering all the situations we have around us and we cannot influence. So here we are, first of all, we are collaborating with the world leader in silicon carbide with Wolfspeed, as we are using the Wolfspeed chipsets, silicon carbide chipsets. But in parallel, we have also developed our own silicon carbide chip. We started with this development quite a while ago. Kind of first trials were done more than 10 years ago. And now we have a 1.2 kilovolt chipset silicon carbide available from Hitachi Energy, what is electrically matched to the one of Wolfspeed. It's, of course, different topologies, but it is electrically matched. And that means you can qualify both modules, the RoadPak with the Wolfspeed chip inside and the RoadPak with the Hitachi Energy chipset inside. If you have once done this qualification, you can seamlessly change between these both RoadPaks with the different chipsets as they are electrically matched. In addition, as already mentioned, for the 400 volt area, we have the 750 volt chipsets with the same configuration. In general, we can say it's always a half bridge. It has a temperature sensor in, and we are using, for the reverse conducting, we are using the improved body diet, what comes together with the MOSFET. As there is also a trend to go towards lower power, we will be adding the RoadPaks XS, the smaller S size, by end of this year. It's 2x4 chips. It is also a smaller footprint. It doesn't make sense to have the same footprint, the same outer dimension with only 8 chips inside, and therefore we decided to make it smaller. That's just as an outlook and as an overview. Good, let's move to some technical details, to some setups, what we are using within the RoadPak. If you compare the RoadPak with various other power modules available on the market, you will figure out that it is, in terms of volume, it's the most powerful silicon carbide e-mobility module you can get. As already mentioned, these S, M, and L sizes, especially also the current ratings mentioned there, the 580, the 780, and the 980 amps, that's a kind of indication. It is a top-end current. Depending on the application, depending on the cooling conditions, as an example, there might be significant downscalings or a reduction of values required. You will also see that later on in this presentation on the mission profiles. So therefore, it's really important. Contact us, let us know the mission profiles, and we can make sure together with you that you get the right size of the RoadPak itself. The RoadPak is using a sinter die attach, both bottom and top side. It is it's optimized for low strain inductance, as already mentioned. We are as low as 5 nanohenries, what allows you at the end with an appropriate and optimized setup with the capacitors as well as with all the connections to build converters at roughly 10-12 nanohenry strain inductance. We are using a design what is able to handle up to 175 degrees centigrade junction temperature on the silicon carbide chips. As there are some new generations coming, we are already prepared on a module side also for 200 degrees centigrade junction temperature, as it's just a matter of the next chip generation, and we can also go even higher here with the temperature. The connections, the wire bonds, they are copper wire bonds. You can also see that the auxiliary and the main terminal connections, that means the connections from the module to the outer world, they are ultrasonic welded. And we have a directly integrated pin fin structure on the base plate. That means it allows you directly to let the cooling water, the cooling liquid flowing through, water glycol mixture, whatever you have, can directly flow through the pin fin, and therefore, as you will later see, we have an optimized thermal impedance. Paralleling silicon carbide chips, especially up to 10, is quite challenging. It requires a lot of optimization, sometimes adapt the gate resistors, whatever. We invested also once again here a lot of time and expertise in it. Finally, we have a module what is able to have up to these 10 parallel dies, 2 times 10 even with the half bridge setup, per switch 10 dies, and to have an excellent current distribution between these different chips, not only statically, but also in a dynamic switching behavior. And that's exactly what you can see on this graph. What we did here is we built an open module without the epoxy mold compound around, added Rogowski coils around the bond wires for every single chip, and did some static and dynamic behavior measurements. And while you can see on the upper graph still the different colors from the current measurement after the switching, by the way, that's the loop function, otherwise you would not even see that there are more colors. But you see latest after the switching, switch on, switch off, it is it's not visible anymore that there is more than one chip, that there is more than one measurement. It's just a black line, and that exactly tells about this excellent current distribution. And that's done without additional gate resistors. So that's a pure design of the module itself, the balanced and symmetrical design of the module itself. And that's really important for us. Furthermore, silicon carbide is obviously optimized for switching frequencies of 10 kilohertz, 20 kilohertz, whatever you require, and therefore also the different losses, they are of course adjusted or depending on the switching frequency what you have. Let's move on a step further towards the cooling. As already indicated, it's important that there is an excellent cooling possibility available. We built the road mount, as we call it. That's the cooler. One road mount can support 3 RoadPaks. The water is coming in on the left-hand side, is flowing through the pin-fin structure of all 3 modules, and is then leaving on the right-hand side. We did some measurements on this setup. We optimized it also with CFD analyzers, of course. And what we can clearly see, doing that, we reach an interesting hottest chip. It's obviously on the 3rd module in the last row. That's very clear. Also, there is also where the hottest cooling liquid is passing through. And we compared it with different other setups. Of course, you can also do it in parallel. That means you have one water flow through all 3 RoadPaks in parallel. Comparing then the hottest chip, we figured out that the serial cooling is in terms of performance is better. Also, you have a highest chip temperature. And obviously, we also did some analysis with other structure, like this meander structure, what is shown here. And also here, it's clearly visible that the serial cooling structure is the most optimized one. There was a long discussion, especially during the concept phase, either to go with a single-side cool module or with a double-side cool module. We had different thoughts, different studies, obviously, as well. And finally turned out that a single-side cool module with a cooling performance of a double-side cool module makes sense. Why that? If you're building a converter and you have to consider to bring the cooling liquid on both sides and still have an optimized cooling flow, might be very challenging, might lead to long hoses or pipes with a certain danger of leakages. That means you would have then a drop in water, most probably over your inverter, maybe even some PCBAs. And that's something we try to get rid of. So that's one of the disadvantages of double-side cooling. Furthermore, we should never forget, if you have something like a double-side cool module, not both sides, top and bottom side, are transmitting or transferring heat in the same percentage. It's always the bottom side is better than the top side. Therefore, we clearly said, okay, let's invest on one side, do an optimization on one side, and try to get the same thermal impedance as a double-side cool module. What is shown here is the thermal impedance for the hottest chip, as well as the average thermal impedance in a setup where we had cooling water coming in with 65 degrees centigrade. It was a water glycol mixture, 90% water and 10% glycol. Flow rate 15 liters per minute. It's kind of on the upper end. Typically, we say between 8 and 12, but 15 is still okay. And with the full setup, RoadPak L, large, with 20 chips. And you see that we are significantly below 100 Kelvin per kilowatt. And that's exactly the goal we plan to reach, and where we have, even with a single cycle cool module, we have an excellent performance. Furthermore, it's very interesting to understand also that this thermal impedance and the complete thermal behavior is heavily depending on the mixture you're using. If you increase glycol or if you lower the glycol part, it has obviously direct influence on the pressure drop as well as on the thermal impedance. All these experience, all these measurements, they are available on our side and can help you on the end user application side to optimize the circuits and to better understand what is then the real thermal impedance you'll expect over time. RoadPak itself is optimized for various applications. Very obvious, as already mentioned several times, it's optimized and can be used in medium to high-end electric cars, no matter if it's two-axle driven or only one-axle driven. Here it has obviously the advantage that it is small and has less weight, but it has a very high power density and an excellent cooling. As that means it makes everything smaller, but at the same time, it's even increasing the power. It obviously can also be used in charging station. That means to charge these medium to high-end electric cars. Very often these days, the same semiconductors are used, what are also used in the cars, can be used there. Of course, space is also constrained there, but much larger constraint there is that you can really make a kind of small setup also in terms of in-feed and supply. And with the high switching frequency, what you can reach with silicon carbide, you have a chance to make especially the filter components, what you need towards the grid connection of such a charging station, smaller. It can be used for e-bus, e-trucks. If you calculate the power you can get out of a RoadPak L at 1200 volt, you will figure out that it easily fits also for e-buses and e-trucks. It can be used in the e-buses also with this charging pantograph. You might have seen this concept already called so-called TOSA concept, where you have a bus with a pantograph. As soon as the bus is reaching a pickup stop, people are leaving, people are entering, the pantograph can be released for, let's say, 20 seconds, 30 seconds, and the battery can be boosted. Afterwards, the bus can continue its journey, and maybe 5-6 bus stops later, the same can be repeated. It can be used in heavy vehicles, as they are mainly used in mining applications. It can be used in railway, either to drive directly the main traction chain of a metro or for an auxiliary converter, and it is also used in marine for shore-to-ship connections. What we are very proud of, and we never thought about that when we developed the module, but just currently there are some RoadPaks flying around in one of the first all-electric aviation jets. Good, let's move on towards the mission-critical application. I already mentioned our origin as Hitachi Energy Semiconductor is from traction, is from high-voltage DC applications. Typical lifetime in these applications are 20, 25, or even 30 years. We recently dismantled a DC supply station in one of the metro stations in London. And we found there a diode surviving 45 years and would still survive if there was not taken a decision to refurbish this equipment. Now that's part of our DNA, providing reliable, long-living power semiconductors, and the same obviously also applies for e-mobility. There are various requirements. Of course, if you think about a car, a typical car, an e-mobility car, is these days calculated with, let's say, 200,000 kilometers, maybe slightly more, and a typical lifetime of 8 years. But if you think about a car, if you think about a truck or a bus, you're talking about several million kilometers and a lifetime what is typically longer than 8 years. And with the experience we have from the traction, and if you think about the traction application and you think about an e-bus application, you'll figure out that there is a huge commonality between these both segments. And that means also that all this experience we gained from the traction side, that helped us a lot also to build a super reliable e-mobility module what serves the requirement and fulfills the requirements for e-buses and e-trucks. What can be done here? I already mentioned there is a lot about the mission profiles. It's important to understand how the power semiconductor at the end is used in the e-mobility application. We are working here with so-called mission profiles, also mission profiles telling the current over time, what is used in typical mission profiles, like here 2 examples. One is German Autobahn highway application. And then you have the speed race. Speed race, you see there are quite some current peaks. That means really fast acceleration. A lot of torque at the end on the motor. Make a good feeling if you press the pedal and you see immediate response. But of course, on the power semiconductor, you will have high current peaks. These mission profiles from certain application, we can convert to temperature profiles. So we can take these currents, we can take the environmental conditions, motor conditions, cooling conditions, and we can calculate the junction temperature of the power semiconductor itself. What is done here, you see junction temperatures up to 170 degrees centigrade, especially in the lower example with the speed race on the Autobahn. We are a little bit exceeding 150. Keeping in mind that 175 for the current silicon carbide chip generation is the maximum, so we're still in a safe operating area here. And now it would be extremely interesting how many times you can survive such a mission profile, to understand, okay, I can survive the 8 years and the 200,000 kilometers, and to make a statement on that. And that's exactly what I'd like to show on the next slide. Let's start here more on the right-hand side, more on the right part of the slide deck with these lifetime models. We took several RoadPaks, built it up into our testers, and we let them run for a long time. We did 2 tests as they are defined per automotive standard AQG 324. There is so-called PC min tests, what means you have T on, T off, so you switch on, let it on for smaller than 60 seconds, and then you switch it off, let it off for less than 60 seconds, and you switch it on again, and you do as long as the device has not failed. So you just repeat. And then you have the same for PC sec, where is a smaller turn-on cycle, where you switch on and off 5 seconds, and also repeat it as long as there is no failure. And we have been performing this test. And you will agree with me, that's kind of ultimative lifetime test. You do it up to the failure, also just let it run, and you wait till it fails, and then you do a failure mechanism analysis, and you try to figure out why it has failed. And we did that for the PC min with a delta junction of 115 Kelvin as test 2. That would mean if you have a kind of 45 degrees centigrade cooling water coming in, and you add 115, you will be at 160 degrees centigrade junction. Also 15 degrees below the maximum, but you would run like this, and then we reached 145,000 cycles. The same and even more impressive is the PC sec result with a delta junction of 90 Kelvin. That means let's assume you have 65 degrees centigrade cooling water inlet at 90 Kelvin. That means you will end up with 155 degrees centigrade on the junction. And here we reached 4 million cycles. That's at least a factor 4 more than what we expected. And as we got feedback from various customers, more than factor 10 of a usual e-mobility module. And so therefore, really all about reliable solution for e-mobility applications, having a superior module with an extremely long lifetime, surviving many of these power cycles. And now we can do the transfer from these lifetime models to the previous discussed mission profiles and temperature profiles. And we can take exactly this junction temperature profile and can calculate based on a rainflow analysis, as it is once again defined in AQG 324. We can do a rainflow analysis and can determine, okay, what is at the end the overall life cycle of this power module. And it also gives us obviously an indication at the end on the fit rate. So based on that, if you have very appropriate mission profiles and we make all these transfer, first the transfer to the junction, then with the lifetime model, what is once again, it's measured. Also these tests, they were running a long time. You can calculate by yourself. It was blocking our test lab quite a long time to reach these results. And then we can directly conclude on a fit rate for the specific application, for the specific mission profiles. Furthermore, what is very important is at the end, obviously, the failure mechanism. Where did the failure happen? Is it on a chip level? Is it on a module level? And we are very proud to say that the final failure happened on the sinter layers, on top and bottom the chip. Why we are proud on that? You might think that you can never be proud on a failure, but here it clearly indicates that the module itself is built in a perfect way. If we would have a failure on a solder layer, we would have to think about using sintering there. But it's a failure in a silver sinter layer, what per se is a very reliable and also from a thermal point of view, extremely good conducting layer. And we have the failure in a silver sinter layer. Of course, we could invest once again more, doing there more adoptions, even trying to improve. But the 4 million cycles we reached, they are by far enough, good enough. And from our point of view, there is no further optimization required. Of course, you can think about, okay, instead of silver sintering, can we do something what is maybe less expensive, and we can reduce the lifetime a little bit. And based on various applications, that's definitely possible. But it's always good to start with the top end, not to improve. Reducing is always adopt and reduce. Therefore, the lifetime is always simpler than trying to go even higher if you have failed reaching the original target. Okay, that's the overview from my side on RoadPak. Thanks a lot for your attention. It's great that you have been part of this session today. Thanks a lot to GVA for the organization of this session and making it happen. And back to you, Mr. Rehmann.
Thank you very much, Tobias, for this very interesting presentation. This brings us to the question and answer session. You now have the opportunity to formulate your open questions in the chat. Please make active use of it. While our guests have time to type their questions, Tobias, I already have some by my own. First, we have seen an interesting cooler solution in your presentation. Can also existing coolers from the customer be used in addition, and maybe can Hitachi Energy assist?
Yeah, absolutely. Thanks a lot for the question. Very interesting question. The cooler I showed is the cooler we have used and we have optimized for our own test setup, and what can be used as a kind of, let's say, test sample that you can immediately start testing and get first results. We fully understand that in most of the application, there are stringent requirements on this cooler that it fits into the inverter box as an example, and it is no problem to use an existing cooler to adopt it, or even to start with our own cooler, the one we provide a sample as an example, and to optimize it. And based on our experience with all the simulation, with all the data we have available, we can also support you to adopt. We had recently a case with a customer being very interested in an optimized cooler because our cooler was too large, especially on the both sides. There was some fixing plates what were in conflict with another part in the inverter box, and together we invested 2 weeks. The customer came up with a proposal how the cooler could look like. We did first CFD analysis, went through, came back with some suggestions. Maybe you could optimize a little bit there, most probably optimize a little bit there. Optimization was done whenever possible. We did calculations, resimulations, and finally we turned out with a very interesting solution. So that's absolutely something we can help you, where we have the expertise available and where we have the know-how available to find the best solution.
Thank you. Second one from my side. How can you drive the RoadPak? How about the drivers that can be used with the RoadPak?
Yeah, very good point. As many of you might know, for silicon carbide, the gate unit is an essential part. We are talking about fast switching, low stray inductance, but that means also in case of a short circuit, you have very high currents within very short time. And that means you need to have a gate unit being able to detect, first of all, short circuits to react appropriately. You might have some requirements in regards to active short circuit, just to make sure that you reach a safe state in case of a failure. And we have been working together with NXP on a gate unit optimized for the RoadPak itself. It's available within the evaluation kit. That means that together with the evaluation kit means gate unit plus RoadPak plus cooler, as you can immediately start doing measurements and understand the performance of the RoadPak. This NXP gate unit is optimized for the RoadPak. Obviously, there are also other suppliers being very interested in the RoadPak and having corresponding solution. The NXP has also the advantage that they have the so-called segmented switch off. That means during a switch off of the MOSFET, they are changing between different gate resistors, external gate resistors, and are therefore once again reducing the losses by another 8%, what helps a lot at the end, especially if you have a limited battery energy available to drive a certain distance, as an example.
Thank you. Very interesting. I see no further questions in our chat. This brings us to the end of our webinar. If you still have any questions, please do not hesitate to contact me or my colleagues from sales directly. You will receive an email with the contact details of our responsible employees afterwards. As experts in power electronics, we at GVA have, of course, even more to offer than semiconductors. In addition to the sale of a whole range of power electronic components, we develop and manufacture assemblies and systems entirely according to your specifications. usually in the range of a few kV up to the megawatt range. Feel free to visit our website for more information. The best way to follow us is on LinkedIn. This is the fastest way to find out the latest news about GVA and its partners, as well as about our latest expert webinars. Tobias Keller and I thank you for your interest. I would be happy to welcome you back at one of our next webinars. Take care, goodbye, and hopefully see you soon.